Okay, this one here is a problem here we're going to, and again, I can't do all these, but I'm trying to pick, ones that are maybe troublesome or, illustrate the basic idea. And remember, if you get stuck on these, just, reach out. Again, email's the best way to get in touch with me because it'll pop up on my phone and the Halo messages do not. All right, so selecting appropriate distributions here, and I just went ahead and hit the solve feature here, and I'll kind of elaborate on this, why these are picked. But essentially, they revolve around the central limit theorem. In other words, if we sample from a distribution and we keep recording their means and over and over and over, I address this in the other videos, that we have a distribution of those sample means. When we talked about sampling distributions, where X bar follows a normal distribution, and the mean is of the sample means is the mean of the population, and the mean of the standard deviation of the sample means, or the standard deviation of the population divided by the square root of the sample size. And when we don't know S, we still want to use that bell-shaped curve, and we use the T distribution. Okay, so it just kind of depends on what we're given here in the circumstances. Now, the central limit theorem also says that, the X bars, or the sample means, will be normally distributed when, in fact, we have even if the population is not normally distributed. So if the population is distributed normally, we don't have to worry about the sample means being normally distributed. But if we start to get some sort of skewness or any other shape that's going on, then we have to rely on large sample sizes in order for the sample means to be normally distributed. And if you remember before, I gave 15 and 30 as kind of cutoffs. 15, you're okay, as long as the skewness isn't too bad. And once you get above 30, you're good to go, even if we got strong skewness. Okay, now those are just rules of thumb that we follow in statistics. So when we read these here, the sample size is 16, and it comes from a normally distributed population with an unknown standard deviation. That was the case that, okay, well, now we've got a situation where we don't know S or sigma, and so therefore we have to use that T distribution, okay, because that was, again, the given parameters for the conditions, right? And that was the whole reason for the T distribution. Here we do know the standard deviation of the population, okay, and so therefore we're going to use Z, and even though we have 17, it is coming again from a normal population, just like we had above. Down here, we don't know, it's coming from a non-normal population, okay? So what we run into here, and this is kind of a unique situation, because the sample size is so much greater than 30, those X bars are going to be normally distributed. And for the most part, once you get up to 90, your standard deviation in your sample is going to be pretty darn close to the standard deviation of the population, okay, the way variances work. So there's a little bit more to it than that, but that's basically it. So this is one of the rare cases you can use either Z or T. And maybe I'll illustrate that with this T distribution here. For instance, if I go to the right with 90 degrees of freedom and have a tail area of 0.05, and then if I go back, we'll just remember that 1.662. And if I go into the normal distribution, okay, the standard normal with a mean of 0 and the standard deviation of 1, and I go the area to, let's see, I want to calculate corresponding area to the right tail of 0.05, and we had 1.622. Well, here 662. Well, now we have 1.645. So those numbers the T was very close to the Z. So as far as practical purposes are concerned, we could use either Z or T. Now, if this number was a lot less than that, and we would run into problems with the X bars being normally distributed, as well as the T, there's a little bit bigger difference between Z and T. Okay, so if I try another one here, and just to see, that's another very similar one. Let me see if I can get one here with the unclear. I'll keep going here. Eventually we'll get one with the unclear, maybe. Oh, here we go. Okay. So here again, we come from a non-normally distributed population here. We do know the standard deviation. It's 110. We don't have to worry about normality. So since we know sigma, we'll just use the Z value. Okay. But for all practical purposes, it could probably be either one. But usually when you know the standard deviation, we'll just go with the Z. The sample size of 14, and it's from a normally distributed population with an unknown standard deviation, or from a normally distributed population, that's a clear case of T. Now, this unclear part here is we have 15. We don't know what that distribution is. So we're kind of, if it's really strongly skewed, actually, neither one of these are going to be very helpful. I mean, we could run the formula, but again, it would be suspect if that skewness was very hard, very strong, okay, one direction or the other. Okay, so there's a couple examples there for you to go by, and we will see you again next video.